Okay, in the last videos we talked about Riemann sums as a method for approximating the area under a curve. We're going to talk about another type of sum that in general is more accurate than Riemann sums, though it's not guaranteed. Sometimes a midpoint Riemann sum can be more accurate than this. But for the most cases, trapezoidal sums are the most accurate that we're going to be looking at in class. And what they do is instead of using rectangles as our geometric shape, we actually use trapezoids instead. So this is a particular case where we're given a function. This is the line that I got here is y equals f of x. So as you can see, in this case, we have n equals 4 subintervals because we have 4 trapezoids. And if we want to calculate this area, it's no different than what we did in Riemann sums, except for the fact that now, instead of just using base times height formula, we use the area of a trapezoid formula. What that actually means is that we need to calculate all of these heights of sides of our trapezoids, and we need to know the x values which they correspond to in order to do them. So if we look at how we would calculate this area, what we would do is wait for the mouse to turn back on. There we go. We would use the area of a trapezoid. Now the area of a trapezoid I have right up here. It's just 1/2 base times the first height plus the second height. In this case, our base is going to be determined by how many subintervals we have. Up in this picture up here, I called our base delta x. If I move up real quick. Yeah, so you saw delta x. That was the base that we used for every one of our trapezoids in this case. So if we wanted to apply this to calculate the area under that curve, we just apply this formula for the area of a trapezoid. So we would say the integral from our case x1 to x5 of our function would just be this is this portion, 1/2 of the base. But since every single trapezoid has the exact same base, we can just pull that on the outside, and then we just apply our trapezoid formula as many times as we need to. If we do this, what we notice is that f of x2 and f of x2 occurs twice. F of x3, there'll be another f of x3, that'll occur twice. Every single f of x value will occur twice in that formula, except for the two outers. So we can kind of simplify this by just saying it's delta x over 2 times the 1 f of x1, which is our first height. Then we can double up all of our heights in between, and then for the last height, we'll just have one height there. If you write out the entire trapezoid rule, like I did partially in this step, if you write out the remaining 3 terms in that, you'll see that it just reduces down to this equation down below. But I would probably advise against not trying to memorize this formula. If you want to memorize it, that's fine, it won't hurt you. But if you just know what the area of a trapezoid is and you just stick to, I want to calculate the areas of 4 separate trapezoids, and if you know how to calculate the 2 heights or the 2 sides of those trapezoids and you know how to calculate the base, then you can just think of it as an exercise in just calculating areas, and you don't really have a formula you need to memorize. But to each their own, do whichever way you would like. But so let's give this a shot. Let's try to do this for this function again. We have y equals x squared. We're looking between x equals 1 and x equals 2. Let's do it with n equals 4 subintervals. So therefore, if we take the distance between 2 and 1, that's 1. If we want 4 subintervals, that means the base is going to be 0.25, so we know that as before. And what we're going to be looking at is basically calculating these trapezoids. Now, as you can see, when I just draw the shape of a trapezoid, that actually looks like a really good approximation for this function if we just use trapezoids. But use the trapezoidal rule, try to do it on your own. Okay, if you do it on your own, what you should have gotten was that the area was equal to the base over 2, or 0.25 over 2. Then our first trapezoid height is going to be 1 squared plus 1.25 squared. Remember that 1.25 squared comes because our function is x squared. If our function was sine of x, these would reduce down to sine of 1 plus sine of 1.25. The reason we have 1.25 is because that's that x value of that division. Remember, this x value is 1.5, this one is 1.75. So we've added that one, then we'll say plus 1.25 squared plus 1.5 squared. This is what we're getting from the second one. The first one we did right here was from the first trapezoid. Then from the third trapezoid, we'll get 1.5 squared plus 1.75 squared. And then finally, from the last trapezoid, we'll get plus 1.75 squared plus 2 squared. And again, if you look at this formula, we notice that the 1 squared and the 2 squared are all on their own, but the 1.25, the 1.5, and the 1.75 all double. So if you go back to that equation I put in the previous slide, you'll see that it reduces to the same thing. So if you do all of this math, you should get that that area is equal to 2.34375. So again, keep calculating this, keep calculating those areas until you can get this. But again, just like with Riemann sums, I think that you'll find that as you do them a little bit more and more, if you think about them as just calculating areas, the hardest thing is to find out what the heights of the rectangles are, the heights of the trapezoids are, the lengths of those sides. And really, it's just you're using simple area calculations, kind of like middle school math. So like I said, trapezoidal rules, as long as you can get them, they're pretty easy and they're pretty easy to remember. But just like with Riemann sums, a trapezoidal sum is only going to give us an approximation. So if we come back in here, there's actually conditions where a trapezoidal sum will over-approximate and under-approximate. It turns out, whereas with the Riemann sum was related to whether the function was increasing or decreasing, or it related to the sign of the first derivative, our overestimate or underestimate in a trapezoidal rule relates to the concavity of the function or the sign of the second derivative. And as you can see here, using a trapezoidal rule on this top one, that trapezoid, this area of our trapezoid is over what our curve is, so we're getting an overestimation. We're getting more area than we should, and that all relates to when the function is concave up. And as you'll see, we get the opposite for when the function is concave down here. We're not including these two little bits of area right here, so we're getting an underestimate. So again, in summation, you want to know how to calculate left, right, and midpoint Riemann sums and trapezoidal sums, and know when they provide overestimations or underestimations. And if you can do that, you actually have a fairly big chunk of what is typically in the AP exams. There's usually a couple multiple choice questions related to these, and there's almost always a section of free response. And like I said, I mean, this is just a very easy way to get a good amount of points in a free response section if you just think about Riemann sums and trapezoidal sums as just summing up the areas of geometric shapes. Don't try to put any complicated equations into them. If you think about them as just areas, I think they become a lot more simple. So anyway, come to class tomorrow with questions about this if you have them, and we will go over some examples.